What is happening, physical science folks? Today we're talking about balancing equations. We set the ground rules for this before we left for Thanksgiving break, so try and remember back to when we put the Alka-Seltzer tablet in a bag. One of the things we didn't do is measure the mass of the Alka-Seltzer tablet and the water prior to putting it into the bag, but if we had, we would have come up with a total mass for the reaction before things started to bubble and fizz. Now, after the reaction took place, we could have placed that bag on a scale, and you would have recognized that the mass before equaled the mass after. The whole idea behind this is that mass cannot be created and it cannot be destroyed. And so even after the Alka-Seltzer tablet bubbles and new gas forms, the total mass before equals the total mass afterwards. And that's the law of conservation of mass. So when we balance equations, it works in almost exactly the same way. Here's an example. If we're making a skateboard, for a skateboard, if we start off with the parts, 4 wheels, 2 trucks for the wheels to go on, and then 1 deck, right? That eventually equals a completed skateboard. You can't have any extra wheels at the end that we didn't have at the very beginning, and you can't have any pieces missing either. Everything we start off with has to equal everything that we end up with at the very end. And that's the law of conservation of mass. So balancing equations works in exactly the same way. Here's our basic equation. Everything on the left-hand side are reactants, and everything on the right-hand side are products. Now that only applies when the arrow is pointing in that direction. The arrow always points to the products. There are some situations where there'll be an arrow pointing back in the opposite direction, but I'll let you know when those arise. So, for example, when things burn, we have carbon and we have oxygen in order for them to combust, and it leads to the production of carbon dioxide, and here is what one of those equations might actually look like, okay? Many of you have seen the periodic table enough now to know that our carbon is right here, and that our oxygen is right here, and at the end we have carbon dioxide. But notice something here. We have 1 carbon atom here, and in our product over here we have 1 carbon atom as well. You can't have any new carbon that wasn't there before. We have 2 oxygen molecules here, and we have 2 oxygen molecules here. Everything we start off with has to be in the product at the end. When we balance an equation, you cannot violate that law of conservation of mass. All right, so keep something in mind. Reactants that's everything we start off with. Those are the pieces to the puzzle that are going to undergo some sort of change, and they turn into our products. Those are our new substances that are formed, okay? Remember, for a chemical change to take place, there's got to be some new substance there that wasn't there before. It's going to have different chemical properties than the reactants did at the very beginning. And when we put those together, we get our chemical equation. This represents the reaction that's actually taking place. It shows the relationship between the reactants and the products. And it's like a chemistry sentence, okay? We take our letters from the periodic table, we put them into words when they bond, and then our chemical sentences are what we're looking at now and making sure that they're completely balanced. All right? So is mass really conserved? It absolutely is. Here, 1 carbon on the left in the reactants, 1 carbon on the right in the products, and then 2 oxygens on the left as reactants and 2 oxygens on the right as products. Regardless of how complex the equations get, the law of conservation of mass cannot be violated. All right? So here's an example. This one looks a little bit crazier. What we have to do is take inventory first, right? Find that arrow, and this divides our reactants on the left from our products on the right, and those are the things that have to be balanced. So if we take a look at each individual element, remember each capital letter, there are 2 nitrogens over here, there are 2 nitrogens over here, okay? There are 4 hydrogens here, and there are only 2 hydrogens over here. So we know that our hydrogens are not balanced right now. And we have 2 oxygens on this side and only 1 oxygen on this side. So things currently right now are not balanced, right? Our nitrogens are okay, but our oxygen and our hydrogen don't match up. So in an equation like this that is not balanced, we have to do something about it. And the only thing that we are allowed to do is place coefficients, okay? Whole numbers in front of any part of this equation. You could put a coefficient here, and it would apply to the nitrogen and hydrogen right here. You can put a coefficient here in front of this oxygen. You can put a coefficient here in front of the nitrogen, or you can put a coefficient here in front of this H2O molecule. But that's all we can do. We don't have to move around or adjust the equation itself. It stays the same. The only thing we do to try and make things balanced is put coefficients in these areas. Okay? So here, for example, I've put a 2 in there just to show you. This 2 applies to everything here within this part of the equation. It has nothing to do with the rest of the equation. So this 2 means I've got double everything I had before. So 2 times 2 gives me 4 hydrogens now. And 2 times 1 gives me 2 oxygens. And that makes that equation balanced now. Okay? We'll practice this more and more. Let me show you one more example here. Find the arrow and draw a line down to separate our reactants from our products. And then we take inventory. There's 1 copper and 1 copper, right? There are 2 oxygen on this side, but only 1 oxygen on that side. So what we're doing is taking inventory. How many of each atom is on each side of the equation? Right? Then we change those coefficients in front to try and make the equation balanced. And then we get to more complicated ones in just a little bit, right? But what would you change in this equation? If the coppers are okay, but the oxygens are not, we have 2 oxygen here, we need 2 oxygen over here, you can put a coefficient here, okay? I'm going to let you try this one and struggle with this one a little bit, and we'll move on to some others as a class and work through them together, okay?